The first task of designing for fire safety is to determine the limit to the size of the building, which is expressed by its floor area, area per floor, and height in feet and in the number of stories. The assumption is that in large buildings, there are typically more people at risk during a fire. Two primary factors to determine the allowable height and area are the general function of the building, occupancy classification, such as assembly, education, business, etc., and the type of construction, which relates to how fire resistant the building elements are. Two other factors that influence the height and area limitations are the presence of an automatic fire sprinkler system, which is designed to prevent the spread of the fire, and open street frontage adjoining a significant portion of the building's perimeter, which provides better fire truck access. Chapter 3 of the International Building Code sets the criteria on how to define a building's occupancy based on how a space or spaces are used within the building. Common building occupancy types include Group A, assembly, Group B, business, Group E, educational, Group I, institutional, Group M, mercantile, and Group R, residential. Occupancy has an effect on the building's height, floor area, type of construction, fire resistance rating, fire protection system, means of egress, and indoor finishes. Chapter 6 of the International Building Code outlines the requirements to correctly classify a building by its type of construction. In general, the more fire-resistant a building is, the larger and taller it is permitted to be. There are 5 building construction types, each with fire resistance ratings that apply to the structure, frame, bearing and non-bearing walls, floor, and roof. Fire resistance rating is defined as the duration in hours for which a passive fire protection system can withstand a standard fire resistance test. A higher rating provides a higher level of safety to its occupants if a fire was to occur. However, the cost of the building to this higher level of fire resistance can be much more costly than a lower construction type classification. In construction type 1, the main structural elements are of non-combustible materials, such as concrete and steel. The roof is also of non-combustible material, such as concrete or steel. Construction type 2 has steel or concrete walls, floors, and structural framing similar to type 1 construction. However, the roof covering material is combustible, such as asphalt-based roofing. Note for type 2B, the main structural elements are unprotected and non-combustible. It is the most common type of non-combustible construction for commercial buildings. Construction type 3 is also called brick and joist. It has masonry-bearing walls, but floor and roof structures are made of wood or other combustible materials. Wood framing can be treated with fire-retardant materials to be fire resistant. Construction type 4 has masonry walls like type 3, but interior framing consists of heavy timber, wood column equal or greater than 8-inch thick, and wood girder equal or greater than 6-inch thick. Floor and roof are plank board. The wood frames are exposed and treated with fire-retardant materials. Construction type 5 is the most combustible of the 5 types. Interior framing and exterior walls may be wood. These buildings are built with wood frame load-bearing walls, floors, and roofs. In type 1 and 2 constructions, the structural elements are of non-combustible materials, usually steel or concrete. Concrete provides higher fire rating capacity than steel. Steel members, columns, and beams may need to be protected by additional fire-resisting materials. These details show some of the fire-resisting construction methods for steel, including concrete encasement, gypsum board encasement, intumescent coating, spray-on cementitious or gypsum-based coatings. Chapter 5 of the International Building Code provides general provisions that are applicable to all buildings in terms of limitations to the building size, which is expressed by the maximum building height in feet, the maximum number of floors, and the maximum building area per floor. These limitations are based on occupancy and type of construction. Note that when a building is equipped throughout with an automatic sprinkler system, the maximum building height is increased by 20 feet. The maximum number of stories is increased by 1, and the building area limitation is permitted to be increased by an additional 200% for buildings with more than 1 story above grade, and an additional 300% for buildings with no more than 1 story above grade. In the rest of this course, an example building will be used to illustrate various design issues on fire safety. The building information is listed here, and it has 2 floors. At this point, the following code compliance tasks can be achieved based on what has been covered so far. The first task is to determine occupancy. Because this building serves university students who do not need supervision in the event of a fire, it should be classified as business, B, instead of education, which is for K-12 students. The second task is to determine whether the building is equipped with an automatic sprinkler system. An automatic sprinkler system is almost always installed in a newly constructed campus building. The next 2 tasks are to determine the type of construction and the building height and area limitations. These 2 tasks involve a trade-off. One can take a trial and error approach by starting with type 2B construction, because it is one of the most economical types, with major building components being non-combustible but unprotected. Referring to this table again, equipped with automatic sprinklers for occupancy B and type 2B construction, the maximum building height is 75 feet, which is 55 plus 20 feet due to sprinkler increase, and maximum height in stories and area per floor are 4 levels, which is 3 levels plus 1 due to sprinkler increase, and 69,000 square feet, which is 23,000 plus 46,000 due to sprinkler increase, respectively. The current design is well under these limits. The second aspect of code compliance is that a means of egress should be put in place. Calculating the total occupant load of a building is one of the first steps to determine the minimum number of plumbing fixtures required and the design of the means of egress system, including the number of exits required, the width and length limitations of egress paths. Chapter 10 of the International Building Code provides a number of uses or functions and their associated load factors, which are defined as floor area in square feet per occupant. Note these areas are measured either in gross or net values. The occupancy load of each floor of the example building is calculated with the load factors defined in the IBC code. The load factor for classroom is expressed as 20 square feet gross per person. The general gross area of the floor, the unshaded area, including bathrooms, stairs, corridors, and lobbies, and the small office are considered as business, which is 100 square feet gross per person, since the general occupancy of the building is B. The medium room has fixed seating, so the actual seat count, 45, is the occupancy load for each medium room. Lounge and lobby are considered as assembly unconcentrated with tables and chairs, which is 15 square feet net per person. Mechanical room is 300 square feet gross per person. Therefore, the total occupancy load is 451 for the first floor and 480 for the second floor. A means of egress is a continuous and unobstructed way of exit travel from any given point in a building or structure to a public street. It consists of three components: exit access from any occupied point in the building to the nearest exit. Exit doors on grade or stairs with a fire-rated enclosure above and below grade. They're at the end of the exit access and the beginning of the exit discharge. Open stairs that are not enclosed within fire-rated walls are typically not considered as exits. Exit discharge, the portion of a means of egress system between the termination of an exit and a public way. The means of egress from point A and B on the ground floor are shown on this floor plan. The exits on the ground floor are the exterior exit doors rather than the stairs. The exits on the second floor are the stairs with a fire-rated enclosure. Once occupants enter a stair in the event of a fire, they are considered safe. The stairs will take people down to the grade level and connect to the exit discharge, eventually to the public street. This stair has an exit door on level 1 directly to the outside, which is the simplest arrangement. This stair does not contain an exit door directly to the outside on level 1. Instead, it exits to a short corridor with a fire-rated enclosure on level 1. In this case, the stair essentially expands to include the corridor as part of the exit. Typically, a floor must have at least 2 exits to permit 2 possible evacuation paths for building occupants during an emergency. The rationale is that if a fire blocks one exit route, occupants can have the second way out. 3 or 4 exits are required, however, if the number of occupants exceeds 500 and 1,000 respectively. 1 exit is permitted for a floor or a space that serves occupants below a certain number. The issue of how many exits have to be provided should be considered for each floor as well as for each space or room of a building. For the example building, which has an occupancy of B, the occupancy load of the second floor is 480. This requires 2 means of egress, 2 stairs. Only 1 door is needed for most of the classrooms in the building because their occupancy load is below 50, except that 2 doors are required for the large classroom on level 1, which has an occupancy load of 69, and these doors need to swing out. If 2 exits are required for an area, such as a floor or a room, the distance between the 2 exits is to be no less than 1/2 of the maximum overall diagonal dimension of the area. If the building is equipped with an automatic sprinkler system, these 2 exits can be spaced more closely. The distance limitation may be 1/3 of the maximum diagonal dimension of the area that they serve. Note that these distances are linear dimensions without following the interior circulation of the building. The requirement remains the same whether it is for an entire floor or for a portion of a floor, such as a room. According to the International Building Code, if a door is a required egress door, it must swing out in the direction of exit travel if the room is to be occupied by more than 50 people. The exterior egress doors must swing out in the direction of egress travel because the occupancy load of the floor is over 49, and the exit door of the stair on grade level must swing out in the direction of egress travel by the occupants from the upper level to the street. This door can swing in and against the direction of egress travel because the room's occupancy load is less than 50. These doors are required to swing out because the large classroom's occupancy load is over 49. The doors need to be pocketed to avoid protruding into the corridor. On the second floor, the doors of the staircases both need to swing in because the egress travel direction is going into the staircase to exit the building. There are two general categories of egress components concerning egress width: stairways and other components such as corridors and doors. To determine the egress width of any component, designers are required to assess three sets of requirements based on occupancy, availability of sprinklers, and accessibility, and identify the width that meets all three sets of requirements. The requirements and procedure for calculating egress width are demonstrated here by using the second floor of the classroom building. The definition of the stairway width is illustrated in this diagram, which is the clear dimension between handrails. This shows the egress width calculation for the stairway per occupant served. Note the total width is divided by 2 because there are 2 stairs. This shows the requirement per minimum egress width. This shows the egress width required by accessibility code. The stairway width shall be at least 48 inches in each stair to meet all 3 sets of requirements. The same process applies to the calculation for corridor width. The corridor width should be at least 72 inches to meet all 3 requirements. As one of the 3 components of a means of egress, exit access is defined as a portion of a means of egress from any occupied point in the building to an exit. The International Building Code provides the maximum allowable length of an exit access travel based on occupancy and the availability of automatic sprinklers. Note that the exit access travel distance is measured from the most remote point of the space of interest to its nearest exit. The worst case scenario in terms of exit access travel distance on this floor is the medium room, which is at the corner of the building about midway between the 2 exit stairs. The exit access travel distance of this room is from the most remote point in the room to its nearest exit, which is exit stair number 2. Therefore, for this medium room, the exit access travel distance is equal to A plus B plus C plus D. According to this table, this distance must be less than 300 feet under occupancy B sprinklered. The exit access travel distance of this classroom is from the most remote point in the room to its nearest exit, which is exit stair number 1. Therefore, for this classroom, exit access travel distance is equal to E plus F plus G. The common path of egress travel is defined as the portion of the exit access travel distance measured from the most remote point within an area to the point where the occupants have separate and distinct accesses to 2 exits or exit access doorways. This table states the maximum allowable common path of egress travel distance based on occupancy and availability of automatic sprinkler systems. For example, in the media room, the common path of travel starts from the most remote point and ends at this point where occupants have access to 2 separate and distinct egress paths. The common path of egress travel of this medium room is therefore A plus B. A dead end exists if the occupants of the corridor or passageway have only one direction to travel to reach any of the building exits. Dead ends will allow a fire event to eliminate access to all of the exits by trapping the occupants in the dead end area. The IBC permits dead end corridor under a certain limit. When there is more than one exit required for a building, there should be no dead end corridors that are more than 20 feet without automatic sprinklers. 50 feet with automatic sprinklers. On the second floor of the example building, this is a dead-end corridor where the occupants only have one direction to travel to an exit. The length of this dead-end corridor is F. In the event of a fire, elevators are designed to return to the ground floor and stop operating. People with disabilities above and below grade may not be able to use the exit stairs to evacuate. Areas of refuge are therefore required in buildings that are not equipped with sprinkler systems. It has been assumed that the example classroom building is equipped with automatic sprinkler systems. Therefore, areas of refuge are not required. However, if the sprinkler system was not available, areas of refuge would be required, and they are usually located on stair landing within the staircase to provide fire and smoke protected areas for those who cannot use the stair, where they can call for help and await evacuation assistance. These areas must provide enough space for wheelchairs without blocking the exit path. If areas of refuge are provided in a stair, the minimum stair width should be 48 inches. Fire protection systems are designed to detect an emergency, alert occupants, and activate building extinguishing components, such as automatic sprinklers and standpipes, to take proper actions to protect people and properties. At the core of a fire alarm system are the detection devices such as heat detectors, smoke detectors, carbon monoxide detectors, multi-sensor detectors, and manual call points. The brain of a fire detection system is the fire alarm control panel, the central hub to receive signals from the detectors and issue alarms to users both by sound and flashing light. The control panel will also send signals to activate automatic standpipe and to certain types of sprinkler systems, such as pre-action sprinklers to extinguish the fire. There are 4 common sprinkler systems. In wet pipe systems, the overhead sprinkler piping is filled with water and pressure. Each sprinkler head acts as its own heat detector. During a fire, the heat causes the core of the sprinkler head to burst, discharging water immediately. Not all the sprinkler heads are activated at once since each head is its own detector. Wet pipe systems are the most common type of fire sprinkler system and the simplest. However, these systems cannot be installed in an environment where the temperatures reach below 40° F. Dry pipe sprinkler systems do not have water in the sprinkler piping, but only pressurized air or nitrogen. The pressurized air holds back the water supply at the main dry pipe valve. When a fire occurs, the air pressure drops and the main dry pipe valve opens to release the water into the piping system. Dry pipe sprinkler systems are designed for an environment with freezing temperatures because water must travel from the valve to the piping and sprinklers. There can be a delay of up to 60 seconds in fire suppression. Pre-action fire sprinkler systems employ the basic concept of a dry pipe system in that water is not contained within the pipes. The difference is that water is held back by an electrically operated valve known as a pre-action valve. Valve operation is controlled by independent flame, heat, or smoke detectors. Each sprinkler head is activated individually. This type of system is often installed in commercial properties such as art galleries, museums, and data centers where if there is an accidental discharge, it can lead to significant losses. A deluge fire sprinkler system is similar to a pre-action system except the sprinkler heads are open and pipe is not pressurized with air. Water is held back by a valve. When the system detects a fire, water is pumped through the pipes. Water is then discharged through all the open heads, flooding the affected area. Deluge systems are used in places that are considered high hazard areas such as power plants, aircraft hangars, and chemical storage or processing facilities. A standpipe system is a network of piping and connections that delivers water through a building for firefighting. It can be combined with automatic sprinkler system, or it may be the only fire protection strategy that allow for rapid engagement with a fire in multi-story buildings. Standpipes are commonly located in staircases.